Alright, so in the last few videos we talked a little bit about increasing and decreasing functions, the first derivative and the first derivative test, things like that. So now we're going to talk about concavity and points of inflection. So the thing with this is it might sound a little more complicated than it actually is, but once we start working with these and do some examples in the next few videos, we'll see that it's really not too bad, and it's actually pretty similar to stuff we've done before. So with concavity, let's talk about concavity first, and then we'll talk about points of inflection. So concavity, there's actually a bunch of different ways to define that, and if you move on to math past calculus, you'll probably take a course where you'll come back to this and talk about it in more depth. But for now, let's define this two different ways. Okay, so there's a notion of concave up and a notion of concave down, and we can define each of these two different ways. So there's a geometric definition and an algebraic or analytic definition, and both are pretty commonly used in calculus. So we'll talk about both of them here, and we'll sort of see how they're related. Alright, so first let's talk about the geometric definition. So the graph of a function f of x is concave up on an open interval I if the graph of f lies above all of its tangent lines on I. So basically, if you have a graph of a function and it's sitting above all of its tangent lines, then the graph is said to be concave up. So, when we talk about concave up and concave down, we really are talking about the graph. But if we want to save time or just, be a little informal, we could just say that the function f of x is concave up. But really, we do mean that the graph. And likewise, the graph of a function f of x is concave down on an open interval I if the graph of f lies below all of its tangent lines on I. So let me talk a little bit more about these, then we'll see some pictures of what that looks like. So I didn't really write it down explicitly, but in order for this to make sense, the function f of x has to be differentiable on I, on this open interval I. So in other words, the derivative of f primed, it has to exist everywhere on this interval. Okay, because otherwise it doesn't make sense to talk about tangent lines, right? So remember, the tangent line, the slope of the tangent line, that's the same thing as the derivative, right? So if the tangent line doesn't exist, then there's no derivative. And it goes the other way too. If there's no derivative, the tangent line doesn't exist, and then that's bad. Okay, so here, this whole definition that we're talking about here sort of depends on these tangent lines, so they have to exist, which means the function f of x has to be differentiable. Otherwise, this just doesn't make any sense to talk about. Okay, so we have concave up and concave down. So let's see, what does this kind of look like here? So we're going to draw some simple examples here. So let's make our x-axis and our y-axis. And we'll just have a simple function f here. Okay, so let's just take a look at this interval starting here and ending here. Okay, so this is going to be our open interval I. From here, whatever number this is to whatever number this is, we don't really care what the numbers are, but let's just take a look at the tangent lines in those intervals. So here, this is our function f of x. Okay, f of x, y equals f of x. Okay, so if we start drawing tangent lines here, what are these tangent lines going to look like? Well, let's take a tangent line at this point here. So this point, the corresponding x-coordinate, that's inside the interval, right? So that's good. So if we take a tangent line there, that's kind of sort of going to look like this, right? So a really rough sketch, so not very good, but we just have I'm going to draw it dotted also, so this doesn't get too cluttered up. But here, what do we see? We see that inside this interval, the graph is sitting above the tangent line, right? The tangent line lies entirely below the graph. Now, this graph might be doing something kind of crazy out here. For example, it might be curving up here and then back down this way, so it might cross the tangent line. But we don't care because that's outside of this interval. Okay, so we're only looking on this interval I here. That's all we care about is what happens on this interval I. And this is the interval that we chose for this example picture here. So we don't care what's happening outside of the interval here, only what's happening inside. Okay, let's take another point in here and let's draw a tangent line there. Okay, so there's a tangent line at this point. All right, and again, we see that inside the interval here, let me zoom in a little bit on this. We see that inside this interval, the graph is sitting entirely above the tangent line here. Okay, so the tangent line is lying below the graph on the entire interval there. Same thing over here. If we draw a tangent line at this point here, we see that the entire tangent line lies below that graph inside this interval here. Okay, So this is sort of just a really simple, picture of what a concave up function looks like. So it's, it's got it curves like this, kind of like a bowl, basically, like a bowl sitting right side up. And all the tangent lines are lying below it in that interval. And again, outside of the interval, we don't care what's happening. We only care what's happening inside of the interval that we're talking about. All right? So let's zoom back out a bit. And let's come back down here. We'll get to these in a minute. But let's come back down here and let's talk about concave down. So now that we've talked about concave up, it might not really be a surprise what concave down looks like. And pretty much just concave up, but upside down. So just to be thorough, let's go ahead and draw some of what that looks like. So here's our x-axis, our y-axis, and then let's put a function in here. Something like that. So this will be y equals f of x. Okay, so our interval, so really this whole thing as I've drawn it is concave down, but let's just take a little piece here. So let's look at this piece, this interval here. So this is going to be our interval I. Okay, so we don't care what's happening over here out to the left of the interval. We don't care what's happening out here to the right of the interval. We're just going to keep our attention focused inside of this interval here. Okay, so this point corresponds to an x, this point corresponds to an x coordinate inside of the interval, so that's good. So what if we draw a tangent line here? Well, then we see the tangent line is sitting the entire tangent line, I should say, is sitting above the function. So in other words, the graph of the function is lying below the tangent line here. Okay, so the graph of the function is below the tangent line, which is what we want for concave down, right? By definition, that's what should be happening. So what if we draw another one at this point? Okay, again, this point corresponds to an x coordinate inside of the interval, so that's good. And again, let's zoom in a bit so we can see this easier. Okay. So a tangent line at that point is going to look kind of sort of something like this. Again, rough sketch, not too good here. So that's our tangent line at this point. We can draw another tangent line at this point, and it's going to look kind of sort of something like that. Okay. And again, we can do the same thing down here, but it's getting kind of cluttered now, so I'm not going to draw another one. But do you see what's happening here? These three tangent lines that I drew here, all those tangent lines lie above the graph of the function f, f of x here. Or in other words, the graph of the function f is it's lying below all the tangent lines. Okay. So for these examples, I only picked a handful, like 3 up here, 3 down here. But in order for a function to be concave up or concave down on an interval, this has to be true for all of the tangent lines in the interval. And there are actually infinitely many tangent lines inside of an interval. So showing that with the picture is going to be pretty hard. So, but that's the geometric definition. So that should hopefully give you, an idea of what these functions might look like. So basically, concave up, roughly speaking, is kind of like bowl shape like this, like a bowl sitting right side up. And concave down is that same thing, just upside down. Okay. So that's the geometric definition. So what if we actually want to, work with these algebraically? What if we want to know when is a function concave up, when is it concave down? What if we want to actually find those intervals? Well, then we have to go to the algebraic or analytic definition, and that's what we have written over here. So let's talk about those. Okay, so here we have, so again, these are also definitions, and these are more algebraic definitions. So f is, or the graph of f, we could say, but just to save space over here, I wrote it like this. F is concave up on an open interval I if f primed is increasing on I. Okay, so what does this mean? This means basically if the derivative is increasing on an interval, then the function or the graph of the function is concave up. Okay, and then likewise, f, the function f of x, is concave down on an interval, on an open interval I, if f prime is decreasing on I. So if the derivative is decreasing on an open interval, then the graph of the function is concave down. Okay, so increasing derivative, then the function is concave up. Decreasing derivative, the function is concave down, or the graph of the function is concave down. Okay, so we're going to talk a little more in detail about these soon, but let's see, how do these relate to these geometric definitions over here? Okay, so what if we take a look at these tangent lines here? Now, as we move from left to right, what do we notice about these 3 tangent lines that I drew here? So let's take a look at this one more closely. So remember, this is the concave up function, right? So let's see, how does it satisfy this definition here? Or let's see if we can get sort of an intuitive idea of how it would satisfy that. So we've already seen that it satisfies this geometric definition, okay? So we have three tangent lines here, this one, and this one here. So let's see, if we move from left to right, what do we see about these tangent lines here? Well, here's our first tangent line, the one that's farthest to the left, or what we should say is tangent to the point that's farthest to the left. Okay, so what kind of slope does this have? It has a negative slope, right? So this line that I'm darkening here has a negative slope, right? It's a negative slope. Now the second tangent line, what kind of slope is that? It's almost flat horizontal. Maybe it's sloping a little bit up, so it's maybe just a barely tiny positive slope. Okay? And this third one that we drew, even further to the right, has a noticeably positive slope, right? So the first one all the way to the left here has a negative slope, and then almost kind of a flat, just a teeny tiny positive slope, and then then the third one has a larger positive slope. Okay, so as we go from left to right, we notice that the slopes are actually increasing, right? So negative number, small positive number, larger positive number. So for example, these could be like negative 10, maybe 0.5, and then maybe 8. Just for example, I'm just throwing numbers out there. But if you think negative 10, 0.5, and 8, those numbers are increasing, right, as we move left to right. So in other words, the slopes of the tangent lines are getting larger, okay? So negative slope, barely positive slope, larger positive slope. So as we move from left to right, the slopes of these tangent lines, they're getting larger. And remember, the slope of the tangent line, that's the same thing as the derivative, right? So in other words, if we move from left to right, the slopes of the tangent lines get larger, which means the derivatives get larger. Or in other words, the derivative is increasing. So f is concave up if the derivative is increasing. And that's what we see in this picture here. Okay, negative derivative, barely positive derivative, and then more positive derivative here. Okay, so as we go from left to right in this interval, the derivative is increasing. So that's kind of the relationship here between this algebraic or analytic definition and this geometric definition here. All right, and then it's pretty much the exact same thing here. So f is concave down on an interval I, on an open interval I, if the derivative is decreasing. So let's take a look at these tangent lines here. We'll zoom in a little bit also. So let's just look at these from left to right. So this first one we drew here. Okay, this first one we drew, what kind of slope does that have? Kind of positive, right? Maybe just a teeny tiny positive slope. The second one we drew, we can tell that has a negative slope, right? That one's sloping downwards, down to the right, so that's a negative slope. And what about this third tangent line? This one is noticeably more negative, right? So as we move from left to right, what happens to the slopes of the tangent lines? Positive, negative, more negative. So in other words, the slopes of these tangent lines, they're getting smaller and smaller, right? They're decreasing. So as we move from left to right in this interval, the slopes of the tangent lines, they're getting smaller. And remember, slope of the tangent line, that's the same thing as the derivative. So if the slope of the tangent line is getting smaller, then the derivative is getting smaller or decreasing. So this concave down function, we see that it does have the property that the derivative is decreasing. And it really just pretty much all comes back to knowing that the derivative is the same thing as the slope of the tangent line. So we talked about that several videos ago, and it's one of those important concepts that just keeps showing up. Okay. So this is the algebraic definition here, but how does that help us? Okay, if we want to actually do some calculations, how does that help us? Well, what did we just get done talking about in the last few videos? We just got done talking about increasing and decreasing functions. And what did we say about those? If we wanted to find where a function is increasing or decreasing, what's that thing we had to do? We had to find the derivative, right? And then find out where's the derivative positive and negative. So let's come up here and just kind of recap that real quick. So ignoring all this stuff, so let's maybe use a different color here. If we just want to ignore all this, so let's section it off. And stepping back from this concavity stuff for a sec, let's recap some of the stuff we talked about in the last few videos. And then we'll see how it relates to this. So if f of x, or let's just say f is increasing, if f is increasing, what does that mean about the derivative? That means the derivative is doing what? Or we shouldn't really say doing, but if f is increasing, then the derivative, f primed, is greater than 0, right? Okay, what if f is decreasing? So I didn't really give myself a lot of room here, but I'll just come over here. So f is decreasing. Okay, so remember we talked about increasing and decreasing functions in the last few videos, and so remember what we learned from that was that if a function f is increasing, then the derivative is positive. Because remember, derivative is slope, right? Derivative really is just the same thing as slope, just kind of a more general form of slope. And if f, the function, is decreasing, then the derivative is negative. Okay. So here, increasing function, positive derivative. Decreasing function, negative derivative. What are we talking about here? Increasing f primed, okay, increasing derivative. Well, what is the derivative of f primed? This is just another function, right? So if we say f primed is increasing, then can we kind of use this to generalize that and say something else that's maybe more useful to us? Because remember, we wanted to know, in the last few videos, we wanted to know when is f increasing, when is it decreasing. You know, we wanted to find those intervals. And to do that, we use this property here, that f is increasing when the derivative is positive. F is decreasing when the derivative is negative. Now what we're saying is f primed is increasing. Okay, so you know, if you want to say this in the most generality, what you could say is a function is increasing when its derivative is positive. Okay, so this function f primed is increasing when its derivative is positive. So f primed is increasing on I means f double primed is positive on I. Okay. So let's kind of zoom out and see the similarities here. Okay, so f is increasing when f primed is positive. F primed is increasing when f double primed is positive. Okay, function is increasing when its derivative is positive. This function is increasing when its derivative is positive. Okay, so that's pretty much, you know, it's the exact same kind of thing here. So before we talk a little bit more about that, let's also just come down here and summarize this. So f is concave down on I if f primed is decreasing on I. So what does it mean for f primed to be decreasing? Well, over here, we know that f is decreasing if f primed is negative, okay? So a function is decreasing if its derivative is negative. So this function is decreasing if its derivative, f double primed, is negative. Okay, so f primed is decreasing on I if its derivative, f double primed, is negative on I. Okay? Okay, so this is what we're going to do, you know, this is how we're going to find out the intervals where a function is concave up or concave down. So remember in the last few videos we were talking about increasing and decreasing. We used the fact that, you know, f primed is positive on such and such interval, so that means f is increasing on that interval. F primed is negative on such and such interval, that means f is decreasing. And, you know, we set up those little sign charts, and, you know, in the next few videos we're going to do some examples where we do the exact same kind of thing, but we'll be using the second derivative instead. So really the math is almost going to be pretty much the same, but we're just going to take one more derivative, but the rest is more or less the same. Okay, so again, to summarize this, a function f, or the graph of a function f, is concave up on an open interval I if the second derivative is positive on that interval. Okay? And a function f, or the graph of a function f, is concave down on an open interval I if the second derivative, f double primed, is negative on I. All right, so in other words, positive second derivative, concave up. Negative second derivative, concave down. Okay, so, you know, now that we have this, we can just kind of sweep under the rug maybe this f prime is increasing on I, f prime is decreasing on I. It's still important just to, you know, to remember that so that you understand the definition, but in the next few videos when we actually do our calculations and things like that, we're going to use this fact here. Okay, this fact right here, and this fact here. So we're not going to refer back to this or this, but it is important to remember those. Okay, so again, make sure you remember those. But for the calculations, it's what's important is this: f double prime positive, f double prime negative. Okay, so that's the introduction for concavity. So we also have to talk about points of inflection. So points of inflection is a pretty quick definition. So let's go ahead and talk about that real quick. So remember when we talked about increasing and decreasing functions, we had that notion of a critical point. And remember, a critical point is a point or just the value of x where the derivative of a function is 0. Okay, so a point of inflection is kind of similar to that, but it's not exactly the same thing. So there are some subtle differences, which is kind of unfortunate, but that's the way it goes, I guess. So let's write down the definition, and then we'll talk about what these differences are. So let's see. So a point C, comma f of c is a point of inflection, or you could just say inflection point. So it's a point of inflection or just an inflection point. Of f, or of the graph of f, if the concavity of f changes at x equals c. Okay, sorry about that. Okay, so oh, and also, I'm not going to write it down because it's kind of out of room a little bit. We can zoom out, so there's room to write it, but it's it should go without saying that this c has to be in the domain of f. Otherwise, it doesn't really even make sense to talk about this, because if c is not in the domain of f, we can't do f of c. Okay, we can't even evaluate it. So in order to be a point of inflection, the x-coordinate, this value of c here, has to be in the domain of f. And also, most people require that the tangent line has to exist at x equals c. So for our purposes, we'll also require that, because that's what most people do in general. So let's say note the tangent line on the graph of f, by the way, the tangent line on the graph of f must exist at x equals c. Okay? So the tangent line on the graph of f must exist at x equals c. Okay, so most people require that, so we'll just require it too. It'll keep things kind of simple. So anyway, so here we have this definition for a point of inflection. So again, a point c comma f of c is a point of inflection of f, or of the graph of f, if the concavity of f changes at x equals c. So in other words, if you have some value of x here where f changes from concave up to concave down, or concave down to concave up, then it's a point of inflection. Okay, so at a point of inflection, the second derivative is going to be 0. All right, or it might be undefined. It's pretty unlikely, I don't want to say impossible, but I want to say it's pretty unlikely that the second derivative would be undefined because of this restriction here. Okay, because if the second derivative is undefined, then I think almost all the time your tangent line is not going to be defined, or the tangent line won't exist. Okay, I don't want to say always, because I just can't think of something off the top of my head right now, but for the most part I think the second derivative would have to be defined. But anyway, we'll cover all that in the next few examples. So how's this different from a critical point? Well, at a critical point, a critical point is just a point where the first derivative is 0, right? Okay, so we don't actually require that the function changes from increasing to decreasing. Okay, as long as the derivative is 0 or undefined, that's a critical point. But for a point of inflection, we do have this extra restriction that the concavity does have to change sign, right? So this definition, it's not really exactly analogous. It's a little bit different because we do have this requirement here that the concavity changes. So if we know that the second derivative is 0 somewhere, then all we have is a possible point of inflection, and then we have to check it using sign charts to see if it actually is a point of inflection. But we'll see some of that in the next few examples, in the next few videos. Okay.